In this video, we're going to take a look at finding critical regions of a geometric distribution. Now, for further stats, you also need to be able to find critical regions for a hypothesis test of the parameter of a geometric distribution. And just like we saw for the Poisson distribution, this does include both one and two-tailed hypothesis tests. Now, you might also find the following results helpful as we work through this video. And hopefully you are familiar with these results because we introduced these in the previous chapter. So if x follows a geometric distribution with parameter p, we can use the following results here. Now feel free to take a note of these, we will use these throughout this video. But other than that, that's everything that we need here for our introduction. So let's get started with some practice questions. So let's get started then with question 1 here. So for question 1, we have a random variable which has the following distribution. A single observation is used to test p equals 0.02 against p being strictly greater than 0.02 using a 10% level of significance. So for the first part of this question, then part A, all we want to do here is find the critical region for this test. So for part A then, we're looking to find the critical region for this test. So the very first thing that I'm going to do here is just start by writing down the hypotheses. I know they're already given here, but I do always like to start just by writing them down myself. So we've got H0 and H1. And this is for the parameter p then. Okay, so for H0, this is for p being equal to 0.02. And then for H1 here, this is for p being strictly greater than 0.02. Okay, now the next thing that I'm going to do here is also assume that H0 is true. So assume that H0 is true. So assume H0 is true. And you might be wondering why we do this. And the reason that we do this is because we have this random variable x here, which is geometrically distributed with parameter p. So if we assume that H0 is true, then our parameter p here must equal 0.02. Okay. So in that case, then x follows a geometric distribution with parameter of 0.02. Like so. Now, what we need here is the probability then that our random variable x here, so let's just write this down. So the probability then that our random variable x here is less than or equal to some value, let's call this c, and this must be strictly less than our significance level. So notice here we don't need to half this because we have a one-tailed hypothesis test for this example. So this must be strictly less than the significance level here of 10%. So that's 0.1. Okay. Now do also notice here, because we have a geometric distribution, the probability that we're looking to evaluate is the opposite of what we'd normally expect here, because for H1, p is strictly greater than 0.02. So normally what we test here is the probability that x is greater than or equal to some value c. However, it always works for the opposite then for the geometric distribution. Okay, so if this was p being less than or strictly less than 0.02, then in that case, this would be the probability that x is greater than or equal, okay, to some value, again, just call it c. So just know here, we do the opposite of what you'd normally expect. It's a really easy mistake to make here. So if we evaluate this probability here, then what do we get? Well, we get 1 minus p, which is 0.02. And then this is the value, this is the power here of this value, which is c. So this is the power of c. And this must be strictly less than 0.1. Okay. So let's simplify the left-hand side here of this inequality. So we get 1 minus here. So the bracket, if we evaluate that, 1 minus 0.02, nice and easy, we get 0.98 there. And that's the power of c. Okay. And this is strictly less than 0.1. So now, if we evaluate this here, we're looking to solve for c, right? Okay. So the first thing I'm going to do then is add 0.98 to the power of c to both sides. I'm also going to subtract 0.1 off both sides. And if you do this correctly, then what you should get here, so therefore 0.98 to the power of c is strictly greater than 0.9. Okay. And to solve for c here, we clearly need to use logarithms. So I'm now going to take logs of both sides, and I'm also going to use the power rule here for the left-hand side. So what that means then is we can bring the c down in front of the logarithm. So I get c log 0.98. And this is greater than log of 0.9. Okay. And then finally, we want to solve for c here. Okay, if we want to solve for c, we just need to divide both sides by log of 0.98. However, we do need to be very careful here because log of 0.98 is negative. So in that case, then, because we're now dividing by a negative number, the direction of the inequality will change. Okay, so just keep an eye out for that. So in that case, c is now strictly less than log of 0.9 over log of 0.98. So log of 0.9 over log of 0.98. So now if we evaluate the right-hand side here using our calculator, if we do this correctly, then what you should find is c is strictly less than 5.2151, so on and so on. So 5.2151, so on and so on. So what that means then is the critical region here. So therefore the critical region. So the critical region here. But what we'd have to do is round down because it's 5.2151. So we round down here. So what that means then is the critical region is x being less than or equal to 5. Okay, so less than or equal to 5. Okay, and there we have it. So that gives the solution to part A. So that's the critical region for this test. So now for part B, let's do that over here. All I want to do here is find the actual significance level of this test. So nice and straightforward here. So for the actual significance level, let me just write that down. So for the actual significance level here, this is simply equal then to the probability that x is less than or equal to 5. Okay, so that's equal to the probability that x is less than or equal to 5. So if we evaluate this probability here, then nice and straightforward, this would be 1 minus p, where p is equal to 0.02. And that's to the power then of x, where x for this example here is 5. So that's the power of 5. And if we just evaluate this here using our calculator, if you do this correctly then, well, clearly this is the same as 1 minus 0.98 to the power of 5. And like I said, just use your calculator. So if you do this correctly, what you should get then is 0.0961. Okay, and there we have it. So that gives the solution to part B, and that gives the solution there to question 1. So if we just take a look then at one more example here, we have question 2, where again we have a random variable which has the following distribution. A single observation is used to test p equals 0.25 against p being strictly less than 0.25 using a 5% level of significance. So for the first part of this question, again, exactly the same as the previous question. All I want to do here is find the critical region for this test. So just as we saw for the previous question, we're going to start by writing down the hypotheses. So for part A then, we have H0 and H1. So for H0 here, again, this is for the parameter P, and P is equal to 0.25. And then for H1 here, so for H1, again, for the parameter P, this is now less than 0.25. Like so. So the next thing that we're going to do here is assume that H0 is true. So we assume that H0 is true. So in that case then, if H0 is true, we have our random variable x here, which follows a geometric distribution with parameter P. But if H0 is true, then P is equal to 0.25. Okay, so 0.25 there, like so. Now what we require here, and do take note of the direction of the inequality here, so we need now the probability that our random variable x here is greater than or equal, so greater than or equal to some value, again let's call this c, and this must be strictly less than our significance level of 5%. Again, we have a one-tailed hypothesis test here, so we don't need to worry about halving the significance level. So this is strictly less than 0.05 here. So now let's solve this probability here. So what we need then is 1 minus p to the power of x minus 1 being strictly less than 0.05. So what have we got then? I've got 1 minus, so 1 minus 0.25 to the power of x minus 1, where x in this example is c, so that's the power of c minus 1. And this is strictly less than 0.05. So to solve for c here, again, just like we saw for the previous example, we're gonna need to use logarithms. Okay. So what I've got here then is 0.75 to the power of c minus 1 is strictly less than 0.05. So now let's take logs here of both sides. And again, let's apply the power rule here and bring this down in front of the logarithm. So I get bracket c minus 1 log of 0.75 is strictly less than log of 0.05. Okay. So now, what I'm going to do here to get c minus 1 on its own is divide both sides by log of 0.75. So we get c minus 1. Now again, be careful here with the direction of the inequality because log of 0.75 is negative. Again, the direction of the inequality will change here. So c minus 1 is strictly greater than log of 0.05 over log of 0.75. Okay, so 0.75 there. Now, obviously, we're looking to solve for c here. So what I need to do now is add 1 to both sides because this is c minus 1. So therefore, to balance the inequality here, we add 1 to both sides. And therefore, c is strictly greater than 1 plus this fraction here. So 1 plus log of 0.05 over log of 0.75. Okay, so log of 0.05 over log of 0.75. So all you need to do here now is just use your calculator. So if you input this right-hand side here correctly into your calculator, you should find that c must be strictly greater than 11.413, so on and so on. So 11.413, so on and so on. So what we need to do now is round up to the next integer, basically. Okay, so therefore, for the critical region, this is x greater than or equal to 12. Okay, so therefore the critical region, let me just write this underneath. So therefore the critical region this is for x being greater than or equal to 12. Okay, so just note here, we round up then for this value. So that's the solution to part A. So now for part B then, it asks us to find the actual significance level of this test. So for part B, let's have a look. And for part B then, it's nice and straightforward again. So for the actual significance level of this test here, so let me just write this down. So for the actual significance level here, what are we looking for? Well, what we want then is the probability that x is greater than or equal to 12. Okay, so we now need the probability then that x is greater than or equal to 12. And nice and straightforward here. So what do we do? Well, this would be 1 minus p to the power of x minus 1, where x in this example is 12. So we do 1 minus p, which is 0.25, to the power of x minus 1, so that's 12 minus 1 there. So in that case, then we now have 0.75 to the power of 11. Put that into your calculator then, and if you input that correctly, what you should get here is 0.0. So we get 0.0422 there. Okay. And there we have it. So that gives the solution there to part B, and that gives the solution to the very last question, question 2. And that brings the end of this video on finding critical regions for a geometric distribution.